everyone. My name is Jong Yoon. The topic I'm gonna cover today is about, cute and small, the robot that collects human brain information as well as able to track humans' response to help and then just give better recovery after a person is suffering from stroke-induced neglect. We are going to start from term stroke and then neuroplasticity. So if cells in the brain some injured due to some stroke, they have a capability to adjust their activities in response to new stimulation or situation. That's why there is a huge demand for scientific evidence on especially how new technologies can be incorporated into clinical practice, especially using repetitive movement to improve functional outcomes of stroke survivors. I'm going to share a quick poster. There are so many, the numbers included here, but needless to say, those numbers, examples, but one quick answer out of here is definitely repetitive practice after stroke is so important. So here is one big central question from our group. Is there any good the recovery therapy accelerating its recovery compared to the current existing therapies? Because the existing therapies are many times particularly boring, hence, they are not engaging enough, so they are not effective. So we are interested in giving different approaches for the patient. We are starting from UL means upper limb motor rehabilitation, especially for the stroke patient. We studied from a gaming robot called the Gizmo 1.0, and then which use a similar, gamifying robot following the path. And then we had multiple, previous, the project ran by one of our, group members, Dr. Murad, and then using, the mobile devices and then also we use some, the VL approaches, which gives more functioning, rehabilitation. So common deficit associated with stroke include motor function, which was part of the previous research, also depression, also visual neglect. So this is our new topic we are going to cover in the following slides. And then we are going to introduce a new robot called the Gizmo 2.0. So starting from Gizmo 1.0, when we were getting the SLCP grant, we were in the middle of building and then completing Gizmo 1.0. This one is dedicated for upper limb motor stroke deficit rehabilitation. So basic idea was, can we provide any, the fun and then engaging the robot that can just help physical interactive elements to achieve and also improve tedious rehabilitation activities. So basic idea was, the robot, guide the patient through physical and so physician drawn path. Here is an example of 6, the contours drawn by rehabilitation physician, and then the robot was programmed to follow that. The basic idea is the patient is allowed and also asked to reach out and then trigger the robot ultrasound sensor, and then the audio and then visual, the feedback will be provided to the patient, notifying them, whether the touch was successful or not. And that will actually, encouraging the patients. So we are able to, count a timer and also provide a screen, especially for very, interesting feedback and then the score, so that we are able to provide, interesting but more engaging, rehabilitation process for the patient. We have created, the Gizmo tutorial, especially to train, give me a second, train the staff from the hospital who will run the experiment. This is actually created by our student.
And then to turn it on, you press it so that the 1 is sticking out. Pick up Gizmo by the base and then place it so that it is centered with the line on the track. In order to scroll through the options, single press the UI button, and to select an option, double press the UI button. And then double press the UI button when the start option is highlighted again, and the countdown timer would start. And then when Gizmo stops, you need to move your hand over the ultrasonic sensor so that Gizmo can register a touch. And in order for Gizmo to register a touch, your hand needs to be under 10 centimeters from the ultrasonic sensor. And here, where Gizmo stops again, um, we won't make contact with Gizmo. Um, and Gizmo will wait 20 seconds, and it'll wait for a touch for that long, and then it will move on to the next position. And it looks like it's the end of the game because we can see that there's a victory screen, and that means it's the end of the game session. And then there'll be an animation as well on the OLED display. And then the score is also shown here. You have the score and the stops. So the score is 3 and the number of stops is 4. And then in order to turn Gizmo off, just press the power button again so that the 0 is sticking out.
Sorry. The name of the robot changes from Gizmo 1.0 to 1.1. In addition to the color that previously black and blue, now is orange. The main difference between these 1.0 and 1.1 was we went to the hospital and then met the rehabilitation the doctor, and then we got their feedback, and then we changed the user interface, also added more variables. Previously there was pre-programmed, and then we are not allowed to change any variables during the experiment. But now we are able to change time to wait or time to move. All of them are randomized so that we are able to extract more valuable information out of this experiment. In addition to the video we created, we build a human step instruction manual, starting from the appearance, how to operate, how to program, how to replace batteries, and then how to change the toggling between interface, and also even how to interact with the robot, and also the charge the battery, and so on and so forth, so that we are not missing any important information between transition from our lab to the hospital setting. The future plan, we received ILB approval about 2 years ago. And then once we have enough number of human subjects collected, we are going to run human patient tests led by Dr. Bernal. He is MD, also rehabilitation medicine. Hopefully we can do that first half of this year. So let's move to the second robot called Gizmo 2.0. And then we are focusing more on called hemispatial neglect rather than the motion deficit. that is going to get responses from the patient. The program of the robot is going to actively change it accordingly. So we'll show the details. So what is hemispatial neglect? If you or a person get a damage to a portion of your brain, if fail to get enough the blood flow that region, and then if that is the area which governs the awareness, we call this the parietal region. So if you remember, there are multiple regions in the brain, like a frontal, central, and then occipital. Especially the middle part called the parietal region is going to in charge of the spatial awareness. So if you are getting some interruption, the flow of blood to the, for example, in this case, right parietal lobe, the problem is the failure to acknowledge the object in the field contralateral to the region. That means the left side. So here is the right side parietal region. If you have some issues with this part, you have some issues, having some awareness on the left side of your part. But interesting thing is, it is not about how you see object. There is no perceptual deficit. That means your the visual receptors are all intact, and the occipital lobes also working fine, but you are simply not aware of the part located on the left side of your part. So for example, if you are asked to mimic the left side figures by drawing, then you only draw the second half, especially only right side. That means you are missing the left side of your part. So after a stroke, more than half of stroke survivors experience hemispatial neglect, and then it takes some time to recover. So outcomes are variable. So therapy may improve outcomes, but if you are not doing your rehabilitation correctly, you may have long-term disability. So this is how we can measure this person has a visual or hemispatial neglect. From the first, the image, if we are asking a patient to draw a center line between these two extreme parts, the patient don't recognize the second left half, so the line is going to be 1/4 from the right. And also, the second figure shows that, the patient only detect only the object located on the right side. So here is our solution. Can we create a small, robot? It is responsive to your brain activity, at the same time able to track the attention of the patient, that will help the robot, and then that help the patient regain the attention. So it is going to move back and forth, and then moving between attention and attention zones. So here is more details. The robot is going to move back and forth in front of the patient. The patient is actually wearing EEG system helmet, and then the robot receives EEG feedback, also face tracking information. The basic idea is tracking patient attention and also analyze the face tracking information through the camera and then EEG analysis, and then understand whether patient is losing or getting awareness of the robot. So if the patient lost the attention or awareness of the robot, that robot can bring in patient attention back to the robot when they lose awareness by producing some noises or vibration feedback to the patient. So if you look at here, we are going to use internet or cloud service in addition to the local devices to run in the future more detailed machine learning analysis. And also we are able to keep track of patients' rehabilitation progress using the cloud service as well. here is a detailed, block diagram of our, the system. The patient is wearing an EEG, that is and runs through the Bluetooth, and also there is the face tracker attached to a Gizmo robot, and then the base station, which is located right next to the person interacting with the patient. So what we are doing is getting EEG, information through the EEG device. Also, the face tracker can, take the photos and then analyze and understand whether patient is having attention to the robot or not. That is, shared between the patient and also microcontroller, and then that information is sent to the Gizmo. And then Gizmo is also send the information about the path and location. And then if the patient is not, paying attention to the robot, gives a signal as a vibration to the robot so that we can regain the attention. And we are going to collect optional output into the cloud. Hopefully, we can build some the machine learning analysis approach so that we can have more information collected from the experiment. So here is how we were able to build the Gizmo robot. You will see 3D printed parts, and then here is the battery pack, and then we use a just nano microcontroller which controls the 2 stepper motors for the motion of the robot, and also 1 servo motor which rotating and tracking the face using a camera attached. So we were able to make this one simply along a straight line back and forth. This can be programmed in real time. That means we are able to give the feedback, accordingly. It moves slow, but we'll make it a little, the faster than this. Okay, I think that should be more than enough. Okay, so I don't know why this one is not following well. Okay, so now we are going to talk about EEG. EEG is a test that measures electrical activity in the brain using small, metal discs, electrode, and then we have some, investment, especially buying this, headset called DSI-7. This is a research-grade wireless dry electrode EEG headset designed for getting information from 7 of the locations in the brain. So if you look at the bottom right side of the figure, and then as I mentioned before, frontal side of the brain is going to be in charge of the the motion and the movement. So we are able to get some motor information out of that. And then backside here is the green colors associated with visual. Occipital lobe is going to handle visual information, but parietal lobe we are interested in is going to have sensory information like awareness. So in this case, this out of the many 10 to 20 international system, the system DSI-7 is able to collect information from 7 regions, 2 from the frontal, 2 from the central, and 3 from the parietal lobes. So that sampling rate is about 300 hertz, and then able to handle 16-bit information. So for us, this dry and also wireless system is good enough to handle the experiment. So 2 students are working on and then getting information from jaw clenching. Actually, jaw clenching is not associated with the visual neglect, but we are interested in and then getting information first because jaw clenching gives lots of input to the system. And then if that is successful, we are going to move to the eye blinking or eyeball motion is going to be done in the next phase. And then we were in the middle of face tracking algorithm. We wanted to track patient attention to Gizmo by analyzing, face tracking. So we get to face pose estimation, means like head pose can be analyzed using 68 landmarks on someone's face, and they get a point which shows in 3D space which direction a person is facing. So we applied heuristic approach to determine if person is looking at or away from the camera. And then I'm going to share a quick demo from made by our student. The image on the screen shows that the robot is actually moving. The motion is done by the servo motor, but able to follow the face. Also, the mention that it is going to now facing at the camera means like having attention or not. I'm very glad that Dr. Yang Peng was our previous speaker because we decided to use called edge computing. To be honest, we don't need to have this one in our project because we don't require so many devices in our system. We have only the robot, EEG system, and then eye tracking camera. So we have only 3 devices. So handling information is not that a lot. But for the education purpose, we decided to apply the edge computing approach, which will generate edge layer. So this will run, the processing, especially time-sensitive data, because cloud computing used to process data that takes longer, and then we may expect some time latency. So edge computing is preferred over clouding when we are running some remote locations or also handling time-sensitive data. So if everything is close to the source of data, and then we still send the information or archive our data in the cloud whenever needed. So in this case, we will definitely use the cloud computing for machine learning. But for the first phase we are working on at this point, edge computing is a good the framework. So some of the students from CS are using Kubernetes to build a computing framework using edge computing approach. This is a summary. We have a patient with an EEG headset, and here we have a base station, and then Gizmo with a camera on. And then we are able to add more devices as needed, for example, smartwatch. So edge computing handles data storage and then the processing data at the edge level, but we are able to send information directly to the cloud if needed to run machine learning model. So you will see here the pink colors is where edge is running, and then the blue ones are where the device is located. And then potentially we are able to add more extra device, which is in the green color. And then the yellow is our main security boundary. So as long as we are running everything at the edge level, there is no data passing this boundary. If needed, we can do that later. So let's summarize what kind of impact this project brought to the program, also the school. Number one, we were able to build a small, engaging robot for the hemispatial neglect patient after they suffer the stroke. And then second, we were able to build a huge educational, sandbox. That means, many of our students, for example, CS, CE, ME, EE students were able to play with different devices and different architectures and different, the disciplines within a simple, project. And then our project was chosen as one of UW Tri-Campus Community College research initiatives. And then is an example for STEM transfer partnership. So this one helps one of our key barriers to low-income student, and then transfer from community college to four-year institutions in the STEM field. Some of our faculty members of the team joined and contribute to the STP coaching sessions. Thank you so much for that. And then we wanted to use some data, got this project to be used for the submission of a bigger grant application to NIH in 2023. And then this is what we are going to do for the future, especially using Gizmo 2.0. We'll collect EEG and face tracking data to find strategy that can detect, brain signals to change, robot movement. And then we are going to add more devices and then computing nodes for the edge computing, as well as cloud service. And then we will also consider definitely patient privacy and data security. That is going to be a big, interesting topic for CS student in the future. And also we are able to add more, for example, facial expression. Approximately, more than half of human communication rely on, facial expression. So understanding and adding this one to the analysis of the feedback awareness is going to be an interesting topic. So I really appreciate all the PI investigators. I was with students for the Gizmo building, and then Dr. Pierre Murad, and also Lena Lapiana. She is BS from UW-B, now currently at UW Seattle. They helped us getting the EEG machine and also combining eye tracking technology to the robot. And Yang Peng and Erica from both UW Bothell Computer Science helped us building the computer science, the device programming as well as edge computing. Also, I really appreciate Jody Ollie from the nursing school. Also, Dr. Bonnell from UW Seattle Rehabilitation Medicine. Okay, so also I'm gonna appreciate all the students join the team and they contribute their time to build the robot, 2 different robots. 5 ME students got financially supported. And then also for the edge computing, 3 CSS students, undergrad students, complete their capstone design project using edge computing. And then we have Josh, who is working on creation of edge computing environment. And then we have the Luca working on 2 the tasks. One is face tracking, also EEG, also along with Miriam. You can see those 2, Miriam and the Luca, wearing the EEG headset. Also, in terms of cybersecurity, Adisha is addressing cybersecurity issues relevant to Gizmo's deployment at Harborview. And I think that's all about the presentation. I really appreciate your attention. So any question? And last final thing, I want to share this figure. It's interesting. Sorry, Pierre, your face is here. This is the fate of biomedical engineers. If you are, biomedical engineers, you have to use you as a hamster at the first place. EEG is non-invasive, still, hurts, see the little bit, the mark on Pierre Murat, the forehead. I think that's all. Thank you so much. I appreciate your attention again.